class. So it's actually given in a much better manner as compared to the derivation that I had given previously. Okay. So what I'm going to do is I'm going to derive it completely today. So I'm just going to share a file here. So actually we'll begin with a little preview about your whatever we have started until now. I'll just revise once again, right? So first thing, I hope you remember, that is your Snell's law, and how does what is the optical fiber, your core cladding, what is the refractive index of core cladding, and remember here we'll talk about propagation of your light rays inside your optical fiber. And when you talk of propagation of light rays inside of your optical fiber, it may be of two types, that is your rectangular slab or your cylindrical waveguide. Okay, so once the light enters into the waveguide, it becomes your mode, right? I told you in the last class we will talk about modes inside the waveguide, right? So for rectangular it will be different, for cylindrical it will be different. So now before that, you need to be thorough about what is your reflection refraction, which we have discussed quite some time. But since I think many of you have not understood properly about the acceptance angle, and then of course the numerical aperture, which I had just told you in gist. So I'm just planning to say it once again properly. Okay. And still, if you are, I'll be sending you the notes. And since the PDF is actually not opening, and I'll send you the notes soon. I'll scan it again. I have got a new book this time, and I'll scan it again and I'll send it to you. So don't worry about it. So I'll just repeat once again about what are the assumptions, the criteria for light to propagate inside a optical fiber. Okay. And before that, what is like your reflection, refraction, just once more, so that if at all someone has not understood, I don't want them to be in a dilemma and not. I know many of the students have this thing of not speaking in class. So that's the reason why I'll just say it once and for all, and I expect you all to please pay attention. So let's say this is your medium, okay? Let's say this is your medium. This is your N1, that is your core, and this is your N2, that is your cladding. Okay, so this side, and whenever I write down N1, it is core, and whenever I write down N2, it is cladding. Just remember this again once and for all. When I write down N naught, that will be for your air. So when I write N naught somewhere, that I'm assuming it as air. Okay. So now, let's say light is incident over here, okay, and the angle given, this angle, let's say it is equal to your pi 1, right? So definitely the light will get refracted given the condition, that is your N1 should be greater than N2. When N1 is greater than your N2, then your light will be refracted, right? So it will be refracted as such given the angle of your refraction as your pi 2. Okay. So from here you had obtained the Snell's law, that is your incidence and this is your refraction. Okay. So you had obtained the Snell's law here, that is your N1 sine pi 1 is equal to your N2 sine pi 2. Okay. Always remember that this is for your ideal case. This is in case of your ideal case. What if there is a practical case? You will see that some part of the light, some part is again reflected. So if this is your refracted ray, so this will be your reflected ray. In a similar manner, if you assume all the light to be reflected, partially some will be refracted, which I have told you in the previous class. Now, if this angle of incidence, as you can see, this is definitely your angle of incidence is less than your angle of refraction. This pi 1 is less than your phi 2. Now, as you go on increasing this phi 1 at some point of time, okay, so if you go on increasing this phi 1 up to, let's say, this much, some angle, okay, less than 90 degree, what happens is there will be a refraction. Sorry, there will be a refraction with an angle of 90 degree. This will be a refraction with an angle of 90 degree. Now that angle, this angle is called as your critical angle given by phi c. Okay, so that means it will be your n1 sine phi c is equal to n2 sine phi 2, right? Now this phi 2 is nothing but your 90 degree over here. So that is your n1 sine phi c is equal to n2 sine 90, and that is nothing but your n1 sine. So I'm just giving this so that if at all few people, I'm pretty sure there are few people who may not have understood and they're not saying anything. So that's the reason why I'm just doing everything a little bit elaborate. So this is your sine phi c will be equal to your n2 by n1, giving rise to phi c is equal to sine inverse of n2 by n1. As I told you, do not by heart it as n2 by n1. It is, and n2 and n1 are nothing but your refractive indices of the two mediums. This is the incident medium and this is the other medium. Okay, that is where the refraction takes place. Okay, so just this in your refractive index of sine inverse refractive index of the refracted medium divided with your incidence medium. Okay, now this was a part of your refraction. Now what happens if further we go on increasing an angle? So here what is phi 1 is less than phi 2. Okay, here this is the case where your phi 1 is equal to your theta c. Now we will go to an angle where phi 1 is, we'll go for the next one, that is your phi 1 is greater than phi c. Okay, so if your phi 1 is greater than phi c, so the previous one is phi 1 equal to phi c, that is a critical angle, and much before that was phi 1 less than phi c. So this is greater than. What will happen if it is greater than phi c? Then you will see a reflection. Okay, if it is equivalent to it is greater than your phi c, then you will see a reflection over here. Okay, that means if this angle is phi here, if you go on further increasing, if this angle is equal to your phi, sorry, so in the similar manner, the same angle at which it will be phi, in the similar manner this will be reflecting. So I think this is an appropriate, we have to, okay, if this is the incident angle, this will be your reflecting angle, right? And so that is called as your total internal reflection. Now keep in your mind, you will have your total internal reflection over here. So I'll just write down here your total internal reflection, where this will be your incident angle and the reflection angle will be same. So you will have phi I equal to your phi reflection. Both the angles will be equal. Now you have to keep in mind when you talk about the optical fiber, there are two conditions. Actually, the first condition for light to actually propagate inside the fiber, the first condition is your phi 1 is greater than phi c. Okay, that is the angle of incidence is greater than phi c. Okay, and the second condition being your n1 is greater than. And these are the, and I was speaking. So these two are the conditions which need to be satisfied for your wave to be traveling, or your light wave to be traveling inside your optical wave. Just a second. Need to be satisfied for light waves to travel through your optical waveguide. Okay. So the next thing that comes over here is the acceptance angle, as I told you in the last class. So I'll just remove this. So actually, when you talk of acceptance angles, it's better I draw like in form of your cylindrical waveguide. Let's say I have a cylindrical waveguide. So just imagine this is like in your cylindrical structure. So let's say this is your cladding. These two are your cladding, and this portion is your core portion. Okay. So what happens? So this is like the center line. This is the center line, right? So let's say there is a incident. So this is completely the center line. Okay. So there is a incident ray over here. Okay. So that ray will actually travel inside your optical waveguide, and this is your angle equivalent to your acceptance angle, let's say, which we are representing as theta A. Okay. And this will actually travel inside your waveguide. Okay. And then you will see a total internal reflection, and in this manner it will go on reflecting. Okay. The ray will go on reflecting, and this angle, let's say we are writing it as phi c. Okay. But let's say there is a ray which is actually transmitting, which is actually getting incident at a different angle greater than this. Let's say it is an angle greater than your, this is an angle greater than your theta A. Okay, so since this is also your theta A angle, let's say that this is an angle greater than theta A. So what will happen for this one? It will actually get your refracted, no doubt. Okay, but it will actually get dispersed inside your. So at first there will be one reflection of refraction over here, and then there will be one reflection over here, and it will actually go into the cladding region. Instead of going inside your core region, it will go to your cladding region. So remember, this is your cladding region, this is your core region, this is your cladding region. Okay, so it will go inside the cladding region instead of getting reflected in the core region, right? So eventually it will be lost by your radiation, right? So this angle at which you completely your rays, and always remember all the rays which are getting incident at your interface, it does not mean that it will get transmitted inside your fiber. Sometimes it gets lost also. For example, this one, it will get lost, but this one, it will get transmitted because it is this is the highest, of course. We have taken this as highest, but if it is less than theta A, also it will transmit. Equal to theta A, it will transmit, but greater than theta A, it will not transmit. It will get it will get reflected inside. It will get transmitted inside the cladding region, or may not at all transmit. Okay, so that is the reason why it is called as your theta A. And from that theta A, we will be able to find out what is called as the numerical aperture. So your acceptance angle is the key point in order to find out your numerical aperture, right? So here in when you try to find out your numerical aperture, we'll have like three media over here. I'll just withdraw this. This is the central line of the core. Okay. This line is the central core axis. Okay. So let's say there is a incident ray over here. And the medium here, we call it as the air medium. Okay. And then it gets through, it gets refracted, refracted first and then. I hope it doesn't look as a straight line. Okay. Anyways, just try to understand it actually gets bent away and then there is a reflection over here. Right. So now this is your N naught. This medium, outside medium is, so we deal with three mediums over here. This is your N naught medium. Okay. Inside this is your N1. This whole thing is your N1. Okay. And let's say this is your N2. That is your cladding. So this is your cladding region. And this is your pore region. Okay. And this is your air medium. Now, as we have got like three mediums over here, we will first have an angle of incidence, this as your theta 1. Okay. This angle is your theta 2. This is your theta 2. Okay. This angle is your phi angle. Similarly, this reflection angle will be a phi angle. This is your 90 degree. Okay. So there will be one small triangle over here. Let me mark the points. This as A, this as B, and this as C. Right. Now, if you see inside this triangle, we will see that this theta 2 is nothing but your phi angle is nothing but your 180 minus 90 minus your theta 2. So before that, let us put Snell's law at this interface, the first interface. So if I put the Snell's law at the first interface, I will write down it is N naught sine theta 1 is equal to N1 sine theta 2. Okay. So this is N1 sine theta 1 is equal to N2 sine theta 2. Now we have this phi angle, I can represent as 180 minus 90 minus your theta 2, which is nothing but your 90 minus theta 2, or which I can just write it in a more engineering language, that is pi by 2 minus theta 2. Okay. So now I replace here, it is N naught sine theta 1 is equal to, so from here I can also write, okay, so from here I can write down theta 2 is equal to pi by 2 plus pi, right? So this is your sine pi by 2 plus pi, right? So this becomes your N1, N naught sine theta 1 is equal to N2 cos phi. Okay. Now, if I can replace this and I wish to have everything in terms of your sine function, so this cos phi I can write as your 1 minus sine square phi root over, as you know, sine square phi plus cos square phi is equal to 1. Okay. Now, if this theta 1, the theta 1, if your theta 1 is equal to the acceptance angle, let's say it's a maximum angle. Okay. Beyond which, if you increase the angle of incidence, then the light will not be transmitted inside the waveguide. That is your acceptance angle. So if this is maximum, then the maximum angle of your refraction will be also equivalent, maximum angle of your refraction will also be equal to your phi c. So now I can just, if I have this assumption here, so your N naught sine theta A will be equal to your N2. So here there's one more step here, that is so this is sine square phi over here. So I'm just replacing directly with phi c. Okay. There's one more step over here. I'm just directly writing it as 1 minus this. So now if you remember, our sine phi c is nothing but n2 by n1. Okay. So it is nothing but 1 minus n2 square by n1 square. Okay. So this is nothing but n1 into, this is your n1 square minus n2 square, and this is divided by n1 square, which I take root over, it will become n1. So this is cancelled. So here I get n naught sine theta a is equal to n1 square minus n2 square root over. Okay. You can mark all the equation numbers. This is equation 1. This is, let's say, equation 2. This is 3. This is 4. Okay. So on, if whatever you wish, like giving numbers. This is 5. Okay. And this is, let's say, your 6. So I'll give this equation as equation number 7. Understood? Now here, from here we try to find out what is the numerical aperture. Okay, that is, angle is only the acceptance angle. It's just the angle, okay, which gives a maximum propagation. But numerical aperture means the amount of acceptance, the total amount of acceptance that we define as numerical aperture. We define it as your n naught sine theta a. That means actually there is like a conical structure you kind of form over here. Okay, so it is a maximum acceptance over here. Okay, so it will definitely have a value. So it is n naught sine theta a. So it is equal to, from this function, it is nothing but your n1 square minus n2 square. Now remember, this is one form of your numerical aperture. Okay, this is one form of your numerical aperture, right? So there is another form. There is another function or another way to write it down. That is, we have a function that is called as delta. Okay, and you have to keep in mind that the incident angle should be within this. The angle of incident should always be within this. Okay, within 0 and the acceptance angle, in order to for the light to travel inside the waveguide. Now there is another function in which we can represent the numerical aperture, right? And that is based on the relative refractive index given by delta. Okay, so this is your relative refractive index. Now this relative refractive index delta is given as n1 square minus n2 square divided by 2 n1 square. Okay, this is the basic way to define. Usually, actually, you might say like your delta is equal to, since it's a difference in the refractive index, it should be equivalent to this. Okay, but this is actually not the thing. The factor is this one, right? Since this is a fractional index difference, so that's the reason why we actually define delta as equal to n1 square minus n2 square by 2 n1 square. Or if this is like 2 less than 1, if this value is actually 2 less than 1, too much less than 1, so we can just write it as n1 minus n2 divided by n1, which is nothing but 1 minus n2 by n1. But we will most often take this expression, okay, either of them, okay. So let's say this is your expression number 9. Now to this expression of your delta is equal to this. Now we just try to tamper a bit in order to obtain your numerical aperture in terms of your delta. Okay. So what we do is we have your delta as n1 square minus n2 square. Okay. Since we want this expression in terms of this expression, what I will do, I'll first divide and multiply by root over of 2 n1 square. Okay. And then multiply of 2 n1 square root over. So just multiply and divide both sides by 2 n1 square. So this becomes my del. So delta, 2 n1 square into del to the power half. Okay. So now if I change over here, so it is nothing but your root over of 2, and if I take root over of n1 square, it is n1 into this is root over of delta. So I can write down that numerical aperture is equal to n1 which part? You took the this is your numerical aperture, okay? Leave this side, okay? So this is your numerical aperture expression, that is your n1 square minus n2 square to the power half. I want to do something to this function so that I get it in terms of your delta function, which is your difference in your refractive index, because mostly in your question, you will be given with this function directly. Your delta function will be given to you directly. So you need not have to, do this, that, and then find out. You can just directly use this function and find out the numerical aperture. Let's say only your refractive index of the incident is given and your delta is only given. So what will you do over there? So directly, you can use this expression and find out the value of the numerical aperture. So I'm just trying to derive it. So you have this n1 square minus, where's my cursor? Yeah. So you have this n1 square minus n2 square root over, right? So how will I get this expression? I have to divide and multiply by 2 n1 square, okay, inside this. But since there is a half over here, what am I doing? I'm dividing and multiplying by root over of 2 n1 square, okay? So to this expression, I'm actually multiplying like this here, dividing and multiplying. So the same thing is written over here in a more engineering sort of a way, right? So inside this, now this has become your delta function, and I'm just, simplified it further, and this n1 square root over is nothing but your n1. This is your root 2, this is your root delta. So in the most simplified manner, you can write in n1 2 delta root over. You can just go through it once more. Let me just zoom out. Okay, this is too much zoom out. Sorry, I'm unable to zoom it out. You can see it from here. If you're still not able to understand, let me know. All of you understood?
Yes, ma'am, understood.
Okay. I'm about to give you a file over here. I'm about to give you a problem. So could you please note down the expressions? Have you all noted down the expression? You can write in the chat box, please. You need not unmute all the time. You can write in the chat box. You all have written down the expressions? Okay, fine. So after this, I'm about to give you a problem. Okay. So I'll see if you can. If you're not replying to this, then definitely I'm not marking your attendance at all. So take down the ray theory analysis. It has got a refractive index of 1.5. So the core refractive index is given as 1.50. Okay, and that of your cladding is given as 1.47. Okay, so you have to find out the critical angle at the core cladding interface. Remember, the interface is really important. If I say the air core interface, you have to give it in a different manner. If I say your core cladding interface, it will be different. So this is your core cladding interface. So please be careful. Your question should possess this information. Else you have to write down in both the functions. Okay. The second one is numerical aperture of the fiber. Okay. Then the third one is the acceptance angle in air. For the fiber. As I told you, you have to keep in mind the first thing you need to check is before just blindly writing on, finding out that whatever information you have, please try to keep in mind you have to first check the core refractive index and the cladding refractive index. Your core refractive index should be greater than the cladding refractive index, which is at over here. So if at all you're facing any interview or something, please keep in mind you have to, as you know, N1 is equal to your 1.5 and N2 is equal to your 1.07. Okay, so N1 is greater than your N2. So there is a condition that is satisfied. And of course, there's an angle of acceptance angle. But of course, since it has already given you to ask it has already asked you to find out. So that's not an issue. You can directly just put in the expressions and find out the answer. So I'm giving you 2 minutes of time. I want all of you to please solve it and write down the expression in the chat box. Write down the first bit in your chat box. That is your critical angle. What is the critical angle? Of N2 by N1, you have both the information. I hope you have got calculators with you. So it is 1.47 by 1.5, which is approximately equal to, I think, 78.5 degree, and many of you got 78.51 or 78.53 or 78.52. Okay, so I'm just approximating it as 78.5 or 78.5, whatever it is, it's correct. So now please write down what is the value of the numerical aperture. We have got your N1 and N2. So the expression that we have with us, that is expression number 8, equation number 8. That is your N1 square minus N2 square root over. So how much you got? 0.29, 0.3, 0.298. Okay, angle. So acceptance angle is all of it.
Acceptance angle. It's acceptance angle.
Got it. So acceptance angle is 17.356. Okay, let me 13.356 is the acceptance angle obtained. 34.7. You doubled it somehow. 34.7. Somnath, how did you get 34.7?
Ma'am, you asked, I think, acceptance angle.
Yeah, acceptance
angle not asked. Critical angle is 17. Means the TIR occurring above 17 and.
No. 1 second. You have written acceptance angle as 34.7. How did you get so?
Ma'am, I applied the formula.
Yeah, that is sine inverse of numerical aperture.
Sine inverse of numerical aperture by sine inverse of numerical aperture and n naught.
No, this is your no. Here the question not n naught. The question here is given for your core cladding interface. That's what I told you the first thing, isn't it? That's the reason why I wrote here core cladding interface. See, the expression which we used earlier, it was one second. Megan, I'm coming to that. Okay, so it was your n naught sine theta a, right? Understood? Okay, fine. But here the question is for what is your but the expression for your that n naught sine theta a was equal to your n1 square minus n2 square half. I am unable to show that over here. You can check it if you have noted down. It is your n naught sine theta a was equal as per equation number 7, that was equal to your n1 square minus n2 square to the root over, which is same as your numerical aperture. Okay, I'm just writing it here. It was your n naught sine theta a was equal to your n1 square minus n2 square half, right? We found out your numerical aperture was equal to this.
Yes, ma'am.
Right? So what will be your theta a then? Okay, I didn't write an expression there. So this is nothing but your, yes, correct. N naught is equal to 1. So it is nothing but your sine inverse of numerical aperture. Yes, correct. This was equal to your 1. So this is your sine inverse of your numerical aperture. So what is the sine inverse of 0.3? So this is your sine inverse of, if I approximate it as 0.3, or if I take it at 0.2983, whatever it is. Actually, we try to keep it up to 1 or maximum 2. Okay. So let me just put it as 0.29. Let's say 0.29, or find it as sine inverse of 0.3. How much are you getting?
Hmm? 17.4.
17.4. Yeah, I want to answer from actually Somnath. Somnath, you understood? Because
Yes, ma'am.
understood, right? So that will be your sine inverse of numerical. It's simple. Sine inverse of numerical aperture, which you are getting as 17 point. How much? Let me see the chat box. 17.4, 17.337. Okay. So 17.4 or 17.337. Okay, so approximately we can write it any of them. So 17.4, 7.35, whatever you say, fine. So you can take that, because those who have taken 0.3, they will be getting as 17.4. For these, you'll be getting 17.356 and so on. Okay, so both of the case it is correct. Okay, so this was your first problem. Then we have another problem here. We'll just solve this problem and then we'll take a little bit break. the second problem. Now, before going to the second problem, okay, before going for that, I have to give you one more expression. The expression of your solid angle, solid acceptance angle. You know about your acceptance angle? That is your theta A is equal to sine inverse of Na. Then there is one more thing, that is your solid acceptance angle. Which is given as this, what do you call, psi or something, okay, which is equal to, for air, it is your pi theta A square. Or that is also, we can write it as pi sine square theta A. So just remember it as pi sine square theta A. That is nothing but your okay. Just keep in mind. Just remember this expression. These two. Okay. Forget about this. Remember these two. Okay. The problem is a typical relative refractive index difference of an optical fiber designed for long distance communication is given as 1%. So that this is given as 1%. Okay. Find out the numerical aperture. The question is asked to find out the numerical aperture and the solid acceptance angle. Numerical aperture you have to find out, then the solid acceptance angle in air for a fiber where the core index is 1.46. So I'm just writing it straight. N1 is 1.46. Further, you have to find out the critical angle at the core cladding interface. At the core cladding interface. Okay. You have to find out the critical angle at the core cladding interface. So that is the question. Find out. Do you feel like there is any missing parameter in the question, or everything seems sufficient? Is there anything missing? Any parameter which is missing? Respond in the chat box. What is no taken here? What is no? Oh, N0. Sorry. N0. N0 is always 1. N0 is always 1. N2 is missing. Okay. Anyone else? Anything missing? N2 or any other who's agreeing that N2 is missing? I mean, missing in the sense that is required for finding out the finding out the numerical aperture, for finding out the solid acceptance angle, and finding out your critical angle. Something which is missing. Okay, so I'll tell you that okay, only one is N2 missing. What about others? You all feel that all the information is sufficient?
No, N2 is not missing.
Okay, so that means N2 is not required for whatever you seek to find out. It is not required. So let us assume that N2 is not required. Try to solve it. Try to solve this. Now, you have to keep everything in mind, which I have told earlier. That is, with respect to your relative refractive index, there were two expressions. There were two expressions for your relative refractive index. Please do not forget that. The first expression was for your general one, that is n1 square minus n2 square by 2 n1 square. There was another expression that is n1 minus n2 by n1 if delta was too much less than 1. So I'm just giving you a hint already, though I was not supposed to, but I'll just give you a hint here that delta was your n1 square minus n2 square by 2 n1 square, or there was one more expression that was n1 minus n2 by n1, which is equal to 1 minus n2 by n1. Okay. If your delta was 2 less than 1, and here your delta is given as 0.01, which is actually 2 less than 1, so you can actually take into account this expression. That's the reason why you did not need the n2 over here. You can directly use this expression. I mean, n2 separately is not required. Okay. So please solve this. Will Okay, solve it. There is no need to take a break or anything. Solve it. You can find out the numerical aperture from your expression number 10, if I had marked it as 10. I'll give you some time to think about it. Let's say 10 minutes. 10 minutes, try to solve it. Understand the question properly and please solve it after that. Okay? Recheck everything that you have written. First, write down what is your NA. Okay? Let's say this is A, this is B, and this is your C. So you will write down A, B, C. What is it? Okay. In your chat box, please write down what is the value of A, what is the value of B, and what is the value of C. Write it in that manner. All of you solve it. I want response from all of you, and then only we'll go to the next section. I give you 10 minutes. Okay. Okay, so please, there's one request. As I told you, try to keep the value within 1 or 2 decimal places, maximum 2 decimal places. This is a approximated value, so we do not go up to 3 digit or 4 digit. It's better if this would have been an experimental thing, then you could have gone up to 4 digit, 4 decimal places. But here, when you actually write in your test and all, please keep it up to 2 decimal places. Okay. So I would request Shomnath and Shreya, please repeat your answers. And also the others, I have taken up to 3, but actually it is up to your 2 decimal places. All of you, please keep it up to 3 decimal places. Shruti, Sonika, you all have given up to 3 decimal places. Please keep it up to 2 decimal places. 2 decimal places, please. So I'm just removing these, and I want 2 decimal places. How can it be 0.20? You gave me 0.206, I think. If 0.206 is approximated, does it become 0.2? Please keep in mind, be precise. Like Sobhai actually gave his answer in degree, mentioned its degree. So, okay, 81.88 degree. Suparna, good. Subhagya, good. Also the others, 0. So I am taking it 0.13 radians. So this is nothing but your pi times n square. Okay. So it is your pi times 0.04. So from here itself, we can understand it is in radians. So it is your 0.13 radians, or as given by 2 students, 3. Actually, Pooja is also given in degrees. No, sorry, radians. Radian. 1 second. Have you given the critical angle as 81 degree, or you have changed? Supanna and oh, sorry, my mistake. Okay. So the solid angle you had given it, that was a critical angle. Okay. Fine. So we'll keep it as radians. We are not converting it into degrees, and you're not even rectifying me when I'm going wrong. So before finding out your critical angle, since we know we need in n2 by n1, and from this expression, so this expression right over here, we'll just use it. Del is equal to 1 minus n2 by n1. Okay, so your n2 by n1 is equal to 1 minus del, and it is 1 minus 0.01, that is equal to 0.99. So in order to find out your critical angle, that is your sine inverse of n2 by n1. That is nothing but your sine inverse of 0.99. I think 0.99. Let me see how you have written it down. So when it is 81.88 or 81.78, Shruti, you got 80.5?
Ma'am, that's by mistake. I will just correct.
Yeah.
I have actually got 81.89.
Okay, 81.89. Now remember, when you get 81.89 or 81.88, let's say you got 81.89 as maximum of your board, or let's say 81.88 degrees. Since you're engineering students, I request you to please get it approximated to 81.99. degree. See, the approximation is usually done based on like what value you are getting. For example, over here it was 0.206. So we approximated it to 0.21. Let's say you got a value of, I'm just writing over here, let's say you got a value of 0.293. You would have not approximated 0.29. You would have approximated as 0.3. Okay, or let's say it was like 2.8, especially when there is, in such circumstances, you have to approximate in that manner. Okay, so please keep that in your mind. And if, let's say it was, don't say after this will approximate it as 82 degrees, not like that. So since you're engineering students, since we are in engineering, so it is better we keep our values as such, because maybe in your IES exams and all this, you might, get these questions. And trust me, me myself, I'm sitting. The reason why I focus so much on approximation, because in the gate exam itself, I had faced issue because of this thing, of this approximation thing, because we were supposed to give, the numerical value answer inside the box. So even though I was little not that bothered about this approximating thing, so I had faced issues. So I really don't want you to have the same thing. So please keep in mind, keep a note about the approximation of your values.
And when theta is very small, then only this is applicable.
Sorry?
When theta is very small, then sine theta is approximated as theta.
No, I'm not saying that. I am talking about approximating values. If you see over here, I'm not talking about approximating your variables. I'm talking about approximating values up to decimal places. It can be any decimal places, but please be careful how you make the approximations. Right? So this is not just for your exams or anything. Okay, you write down your exams. Of course, the nearest one, whichever comes over, that you will select. That's not an issue. I'm not talking for your online tests or anything. I'm talking about for a longer run. Right? Okay.
Yes, sir.
So the next thing is, as I told you about the modes. Okay. So modes is different for your planar wave, that is your rectangular guide, and mode is different in case of your cylindrical waveguide. Okay. How much time do we have? We have 10 minutes, 13 minutes. Okay. And I'll just tell you what is your mode, what exactly. Just keep in mind, in short, you define your mode as a stable electric field distribution, okay, or sometimes also your magnetic field distribution. Because when you talk, as I'm telling you again and again, when you talk of a wave traveling, it's both the waves that are traveling. That is, electric wave is also traveling, magnetic wave is also traveling. They actually travel perpendicular to each other along the direction of your propagation. That is perpendicular to each other and transverse to the direction of propagation, right? So we'll be dealing with the electric field here. So the stable distribution of the field along the direction, that is, let's say it is x direction. The wave is traveling along the z direction, but the field is actually along the x direction. So the propagation of the varying electric field along the x direction with respect to the dependence on the z direction, that is called as your mode. So whatever I said, I know pretty much it just bounced off your head. So I'll just show it over here. hope you guys are not thinking that, this is some sort of, what do I say? Many of you might be thinking like it looks like this. I hope you understand it is like a cross-sectional view of your core and cladding. Please don't think that, it is like a sandwich sort of a structure. It's like, the rectangular thing. Okay, this is it is actually kind of a sandwich sort of structure, but this is for your rectangular or your planar guide. But in case of your cylindrical, it becomes different. It has oval shape and all. Okay, and as when you talk about your cylindrical structure, then you will have to talk about your step index or your gridded index, right? For here it is, of course, your single sort of manner, that is a step index. But when it becomes your cylindrical waveguide, you have to think whether it is a step index or whether it is your gridded index. Okay. So now when your light waves actually travel, okay, so before that, this is your central line. I have to always give on showing the central line. Okay. And let's say your light ray travels. Let's say light ray has been traveling. So from here, it'll go on showing like this. Okay. So from here, you get like reflected here. Then it will go like this. Then it will go like this, right? So let me just mark here the points. This is 1 point. The same repetition over here. This is 1 point. Let's say this point is A. This point is B. Okay. The angle being here is your theta, right? So now when your light ray is traveling, you have a propagation constant over here, which if we split into, so remember that when you talk of light and a light ray travels inside the waveguide, there are two parameters which change once the light enters this waveguide. Okay, that is the planar guide. So the first thing that will change is your lambda. Let's say there was lambda over here. Okay, there is a wavelength was lambda. Okay, and the propagation constant, let's say it was your k. It is nothing, k is nothing but your 2 pi by lambda. Remember this k, beta, they're all the same thing, but the representation actually changes depending on where they are traveling. Okay, so this is nothing but the k is nothing but your 2 pi by lambda. So don't get confused. Now here if it was lambda, here it was k, but once it enters inside the waveguide, it actually changes. This lambda will reduce and the propagation constant will increase. How, by what value it will increase inside this? So let's say this was this much. Over here, let's say in the air or whatever media it was this much. So once it gets inside the waveguide or a planar guide, so your wavelength becomes, it decreases by n1 times. Why I'm writing n1? Because n1 is the cladding. So your core refractive index, and please keep in mind the light is actually not supposed to travel in the cladding. Cladding is nothing but like a, what do you say? It actually helps in just reflecting the light, because we want two mediums to be there inside it. Okay. That means if something is like going out, for example, how do I say? Let's say a lot of people are going in a track, so there are some boundaries given in the sideway, so that if they're going out of the track, then someone will be there to push them back to the track itself, right? So in a similar manner, so that no one else is harmed, in a similar manner, in order to not lose a signal, and we want transmission, how on earth it's possible for the transmission if the refractive index of the another media over here should be less than the media in the this medium. So that's the reason why a core is constructed. That's the reason why a cladding is constructed. And the refractive index of the cladding is lower than the refractive index of the core, so that the light gets reflected, right? So the light is supposed to travel in the core only. It is not supposed to go to the cladding. But unfortunately, since this is never an ideal case, there will be some portion of light that will actually get refracted. Remember, light gets reflected in the core and it gets refracted in your cladding. Okay, so there is possibility that some portion might be even like getting refracted over here. It loses. We will see how that losses happen. What is the amount of loss? How to find it out? We'll see that later on. So this wavelength actually gets attenuated and it reduces by a factor of n1, that is refractive index of the core, while on the other side, the propagation constant, that is k, it increases by a factor of n. Please keep in mind the propagation constant increases and the wavelength actually decreases. Now, if we actually superimpose this here, so this is, let's say this is your x direction and this is your z direction. Remember, light travels in your z direction. So this is your z axis and this is your x axis. So this splitting, we can write this function, that is your beta z, the propagation, will be your n1k sine theta, and this will be n1k cos theta. This function, that is your beta x function. Now keep in, so I'm just writing here, beta x is equal to n1 cos theta, beta z is, these are the two components. I hope you remember from your electromagnetic field theory. We used to do this a lot of time, right? So here, the thing is, your wave is traveling in z-axis. This component of z will not be considered. The component of x will be considered over here, not the z. So here, if you see from this point to this point, that is your 1, it gets like here and then gets reflected, right? So here you will see that the total phase change will be equivalent to your 2m pi. Now keep in mind this m, that if you come across the different modes, that is your TE mode, your TM mode, this m you represent like TEM, okay, or you represent it as TMM, right? So this m, and this m can range from any value starting from 0, 1, whatever it is. For a standing your standing mode, it will be 0. For next of the mode, it will be like of different value, like it can be your 1, it can be your 2, it can be your 3, but 1, 2, 3 are of the lower modes. In the higher mode, actually it was really difficult, and in the lower modes is more approachable. Okay. So that is what is called as your mode, right? That means a stable field. So here actually the wave is standing. So here whatever is given over here, the wave is standing. That means at the central line, you will see that the electric field intensity is high. As it goes towards the cladding, it goes on decreasing. But at the center, it is really high. But when it goes on going towards the cladding, it will go on decreasing. So that means if I actually show like an electric field distribution over here, if I mark a line here, okay, and try to show the electric field distribution, it will actually come from 0. This is your cladding. Let me just mark this. This is the core portion, and from here is the cladding portion. But as we know, some portion will go into the cladding. So from here, it will be like this, decreasing like this. Okay, so the strength of the electric field will be extremely high, in the central axis, and it will go on increasing towards your core, right? So usually your electric field travels in a sinusoidal sort of manner, of course, along your x direction, along there, but in your x direction. Okay, so that is how you get the value of your z. Your 2m pi is the total phase change. Okay, that is already 230. We will stop over here, and I'll tell you this is your mode 0. Keep in mind this, whatever I have explained here. Here mode is 0. Why? Why the mode is 0? Because along this line in your core, not even like once it has passed through the axis, this distribution. Okay, so that's the reason why this is 0, indicating this is a standing wave. Now it is your job that before the class next time, please come across what is your standing wave. And of course, I don't know whether it was taught to you about the other modes, but we will see what is the TE mode, what is the TA mode, and what this M value stands for, etc., etc. And we will study about the modes in the cylindrical waveguide in the next class. Okay, so time is already running out. So just quickly take the attendance. I'll just mark the attendance. We have no time for roll call today. I'll just mark the attendance. Give me a minute. Okay, so I observed that the number of students at the beginning of the class were 41. After 20-30 minutes, it was 47. Sorry, I mean excluding mine own to just remove it. It was like 39, then it changed into, now it is 49. It was 45 in between. So please do not do this. If you are joining, stay throughout the class, else I'll take the attendance at the beginning of the class, and whoever have joined in the first 5 minutes, I'll just stick to that. So I might do this in the next class onwards. Okay. So thank you all, and have a great day, and please take care of yourself. We'll see you again in the next class. Thank you.